Right now, if you want to drive from Dubai to Dammam, you burn an entire day on the road. 800 kilometers of asphalt through the desert, border checkpoints, fuel stops, and the kind of heat that warps the air above the tarmac. 8 hours minimum. And every single year, more than 11 million vehicles make some version of that journey across the Gulf states, feeding a $250 billion trade corridor that runs on rubber tires and diesel fumes. But under the surface of the Persian Gulf, less than 250 kilometers of shallow, warm seawater separates the coastline of Dubai from the eastern province of Saudi Arabia. That gap has been an open wound in Gulf logistics for decades, and now, a $40 billion engineering proposal aims to close it, not with a bridge, not with a ferry, but with a fully submerged, multi-lane underwater highway driven directly through the seabed of the Persian Gulf. If it gets built, it will be the longest undersea road tunnel on Earth, and the engineering required to make it happen sits right at the edge of what human construction has ever attempted.
The heart of Dubai beats here, where engineering marvels meet the Gulf. Look closer. The future of our world is being built.
The first thing you need to understand is what sits between these two coastlines. The Persian Gulf is not the Atlantic, it is not deep. The average depth across the entire basin is only about 35 meters, roughly the height of a 12-story building laid on its side. At its deepest, near the Strait of Hormuz, it barely reaches 100 meters. Between the UAE coast and the Saudi coast, most of the seabed sits between 20 and 50 meters below the waterline. This is shallow enough to be a massive advantage. The Marmara Tunnel in Istanbul was built 60 meters below sea level, and it cost roughly $5 billion for just over a kilometer of immersed tube. The Channel Tunnel between England and France runs nearly 50 kilometers, but sits mostly within a specific chalk marl geological layer that boring machines could chew through predictably. The Gulf crossing would need to cover roughly 240 kilometers of distance while staying within a relatively shallow seabed. But that seabed is not chalk. It is a layered mix of carbonate sediment, limestone, sandstone, and in places, anhydrite evaporite deposits. Some of those layers are geologically stable, others are unpredictable, and the entire basin sits on top of one of the most hydrocarbon-rich geological formations on the planet. You are building directly over oil and gas reservoirs. Every meter of tunnel route has to be mapped against existing extraction infrastructure, submarine pipelines, and geological fault data that has been collected by petroleum companies for half a century. Before a single tunnel boring machine even touches rock, the geotechnical survey alone would take 3 to 4 years and cost upward of $2 billion. But assume the survey is done. Assume the route is locked. The next question is the most fundamental one in all of tunnel engineering. How do you actually build it? For a crossing this long, there are only 2 viable methods, and the project would almost certainly use both. The first is the immersed tube method. Massive prefabricated concrete tunnel segments, each one roughly 180 meters long, 40 meters wide, and weighing up to 73,000 metric tons, are constructed in a dry dock on land. Think of a shipyard, but instead of building a vessel designed to float, you are building one designed to sink. Each segment is a sealed, watertight concrete box internally fitted with road decks, ventilation ducts, emergency escape corridors, fire suppression plumbing, and structural reinforcement rated for 120 years of saltwater exposure.
The risk here is substantial. A geological anomaly could compromise the entire tunnel structure. We need to stabilize it immediately.
Once a segment is complete, the dry dock is flooded and the segment floats. It is then towed by a flotilla of ocean-going tugboats to a precise GPS coordinate above a pre-dredged trench on the seabed. Controlled ballast flooding sinks the segment slowly, centimeters at a time, into the trench, where hydraulic jacks align it to the previous segment with a tolerance of less than 20 millimeters. The joint is sealed with a rubber gasket system, called a Gina gasket. Then the water between the 2 segments is pumped out, and the immense hydrostatic pressure of the ocean itself compresses the joint tighter than any bolt could. This is proven technology. The Hong Kong-Zhuhai-Macau Bridge used 6.7 kilometers of immersed tube. The Fehmarn Belt Tunnel being built between Denmark and Germany uses nearly 18 kilometers. But this project would require well over 100 kilometers of immersed tube segments, more than 5 times the longest ever attempted. The second method covers the deeper mid-channel sections, where the seabed drops and sediment conditions make dredging impractical. Here, tunnel boring machines take over. These are not standard TBMs. An undersea TBM rated for Gulf conditions would measure approximately 15 meters in cutting diameter, wider than a 4-lane highway. The machine is a self-contained factory. At the front, a rotating cutter head studded with tungsten carbide disc cutters grinds into the rock face at a rate of roughly 8 to 15 meters per day. Behind the cutter head, hydraulic rams push the entire machine forward, while a mechanical erector arm lifts precast concrete lining segments, each weighing several tons, into a ring pattern, bolting them together to form the permanent tunnel wall. A sealed conveyor system removes the excavated rock and sediment backward through the tunnel to a processing facility on land. The machine maintains a pressurized earth balance at its face, meaning the cutting chamber is kept at a pressure that exactly matches the surrounding groundwater and earth pressure, preventing catastrophic water ingress. If that pressure balance fails even marginally, millions of liters of Gulf water can flood the excavation chamber in minutes. One of the most critical engineering challenges of the entire project is maintaining that balance across hundreds of kilometers, while the geological composition shifts from limestone to sandstone to...
The scale of this engineering feat is truly transformative, connecting communities like never before and promising a new era of infrastructure.
...times within the same kilometer. Now, a tunnel this long cannot survive on its own. It needs to breathe. A car engine running inside a sealed tube produces carbon monoxide, carbon dioxide, nitrogen oxides, and heat. Multiply that by thousands of vehicles per hour in a 240-kilometer enclosed space, and you have a lethal atmosphere within minutes. The ventilation system alone is one of the most complex engineering packages in the entire project. The design calls for a longitudinal ventilation architecture with transverse boosting at intervals. Every 3 to 4 kilometers along the tunnel, vertical ventilation shafts rise from the tunnel to artificial islands constructed on the Gulf surface. Each island is a climate-controlled mechanical plant housing jet fans, capable of moving 600 cubic meters of air per second, filtration systems, emergency generator rooms, and fire suppression control stations. The air inside the tunnel moves in a controlled directional flow. Fresh air is forced in from one end, contaminated air is extracted through the shafts, and the entire atmosphere of the tunnel is replaced approximately every 12 minutes. In a fire scenario, the ventilation system reverses section by section, pulling smoke away from stranded motorists and channeling it toward extraction points while maintaining breathable air in the evacuation corridors that run parallel to the main road deck. These corridors are pressurized to a higher air pressure than the main tunnel, so when an emergency door is opened, clean air rushes out rather than smoke rushing in. The artificial islands are not just ventilation platforms. They are the logistical spine of the entire operation. Spaced every 3 to 4 kilometers, roughly 60 to 70 islands in total, each one is a multi-function offshore station. They house the tunnel's electrical substations because the lighting, ventilation, monitoring, drainage, and communication systems inside the tunnel consume roughly the same electrical load as a small city. They house pump rooms because even the best sealed tunnel still accumulates seepage water, and that water must be pumped to the surface continuously, 24 hours a day, for the entire operational life of the structure. They house sensor control nodes for the tunnel's integrated monitoring system, a network of tens of thousands of sensors embedded in the concrete lining, measuring strain, temperature, joint displacement, water intrusion, air quality, and seismic activity in real time. And critically, they serve as emergency access points. If an accident or mechanical failure occurs at the midpoint of the tunnel, 120 kilometers from either shore, rescue crews and equipment must be deployable within minutes, not hours. Each island has helipads.
The next stage is critical. The key lies beneath the surface, a marvel of engineering waiting to be revealed.
Fast response boat docks and direct stairwell access to the tunnel below. Construction of the islands themselves is a mega project within the mega project. Each island is built by sinking massive steel caissons, hollow cylindrical structures, into the seabed, filling them with reinforced concrete, and building upward from a stabilized foundation. The technique is essentially the same used to build offshore oil platform jackets, which is fortunate, because the Persian Gulf has more experience with offshore platform construction than any other body of water on the planet. Saudi Aramco, ADNOC, and the dozens of fabrication yards along the Gulf Coast have been building, maintaining, and decommissioning offshore structures in these exact waters for over 70 years. The labor force, the supply chain, the marine logistics, they already exist. This is one of the project's most significant hidden advantages. You are not building an undersea tunnel in the middle of the Atlantic. You are building it in the most heavily industrialized shallow sea on Earth, surrounded by nations with virtually unlimited capital reserves and an existing ecosystem of marine-heavy construction. But capital and capability do not solve everything. The political architecture of this project is as complex as the engineering. The tunnel would cross international maritime boundaries. It would require bilateral treaties covering jurisdiction, toll revenue sharing, customs integration, immigration processing, emergency response protocols, environmental compliance, and long-term maintenance obligations. Both entry points would need massive toll plaza and customs clearance facilities, hybrid complexes that function simultaneously as highway on-ramps, border crossings, and security screening stations. The Saudi terminal would likely connect to the existing Eastern Province highway network near Dammam, or Al Khobar, linking directly to the infrastructure feeding the GCC railway corridor and the King Fahd Causeway traffic system. The Dubai terminal would integrate with the Emirates National Highway grid, potentially tying into the E11 or E311 corridors. A journey that currently takes 8 hours by road or 90 minutes by air would be reduced to roughly 2 hours of straight, climate-controlled driving under the sea, with no weather delays, no border queues, and no fuel stops. The economic calculus is staggering. Current trade between the UAE and Saudi Arabia exceeds $60 billion annually and is growing. The trucking costs, fuel consumption, vehicle wear, driver hours, and border wait times embedded in that trade represent billions in friction losses. An undersea highway would not just reduce those costs, it would fundamentally restructure the logistics map of the entire Arabian Peninsula. Goods manufactured in Jebel Ali Free Zone could arrive at Saudi distribution centers in hours rather than days. Saudi petrochemical exports could flow to Dubai's port facilities without touching a single surface road. The tourism potential alone, the ability to drive from Riyadh to Dubai for a weekend, would create an entirely new consumer behavior pattern across the Gulf.
This tunnel isn't just a road, it's a connection between continents, a marvel of engineering stretching far below the ocean surface.
And beyond economics, there is the geopolitical signal. The King Fahd Causeway linking Saudi Arabia to Bahrain was completed in 1986 at a cost of roughly $1.2 billion. It carried over 25 million passengers in a single recent year and is now being expanded with a second parallel link because it has exceeded its design capacity. It proved that a physical connection between Gulf states does not just serve existing demand, it creates demand that did not previously exist. An underwater highway between the two largest economies in the Middle East would operate on that same principle, but at an exponentially greater scale. The construction timeline for a project of this magnitude would stretch between 12 and 18 years. The first 3 to 4 years are entirely survey and design. The next 2 to 3 years are spent building the fabrication dry docks, the island caissons, and the TBM launch shafts. Active tunnel construction, the immersed tube laying and TBM boring, occupies roughly 6 to 8 years, with multiple fronts working simultaneously from both shores and from mid-channel island access points. The final 2 to 3 years are fit-out, road surfacing, electrical commissioning, ventilation testing, sensor calibration, safety certification, and the thousands of small systems that transform a concrete tube into a functioning highway. At peak construction, the project would employ an estimated 40 to 60,000 workers directly, with another 100,000 or more in supply chain, logistics, and support roles across both countries. The $40 billion price estimate is conservative. It assumes favorable geology, stable material costs, and no major engineering surprises. The Channel Tunnel was originally budgeted at £5.5 billion and ended up costing over $13 billion. The Big Dig in Boston tripled its budget. Mega projects of this class almost always overrun, and a Gulf crossing would face unique cost pressures from the extreme temperatures, the corrosive salt environment, the hydrocarbon-rich seabed geology, and the sheer logistical complexity of building on open water across two sovereign jurisdictions. A more realistic final cost is likely between $50 and $70 billion, but in a region that has spent over $1 trillion on Vision 2030 projects, on NEOM, on the Etihad rail network, on entirely new cities built from sand, that figure is not impossible. It is simply the price of connecting two economies that were always meant to be connected. The water between them was never a boundary. It was always just an engineering problem waiting for a generation ambitious enough to solve it.
Welcome to the future. This underwater marvel, a testament to human ingenuity, spans across the depths, connecting our world like never before.